In this module, we will discuss how to understand Cartesian vectors in 2 dimensions. Suppose we have a general vector f. It is useful to draw the vector relative to a set of x and y axes. The vector has a component along the x direction and a component along the y direction. We can label each of these components with a vector symbol, one for fx and one for fy. And we can understand the total vector as the vector sum of the components. Note that the components can be added in either order. The x plus y is the same as the y plus the x. So for example, if I understand the fx component then added to the fy component, that's one way to see the vector. Alternatively, I can take fy vector and then add fx vector and get the same total vector. A unit vector is any vector whose magnitude is equal to 1. A unit vector is a so-called pure vector and does not have a physical unit. They describe only direction. So for example, I could say I'm a vector 5 miles in magnitude in the northeast direction. And if I define the vector u as the unit vector to represent the northeast direction, I could then say this vector, which I'll call d, is 5 miles multiplied by the u direction. In general, any vector is a product of a scalar and a unit vector. And typically, we often say the vector is a magnitude in a direction. And so, yes, that's the common way of thinking about it. This vector is 5 miles in the unit direction northeast. But for the sake of argument, we could also define the vector negative 5 miles in the negative u direction. And that would be equally correct and sometimes useful in cases that we'll see later. The Cartesian vector system can be used to indicate directions along each coordinate axis. We'll define I and j as the unit vectors along the x and y axes respectively. And so let's note that each I and j vector has a magnitude of 1. We can write this by the magnitude symbols that we learned in the earlier module. So the magnitude of I equals the magnitude of j equals 1. And as we said before, unit vectors do not have physical units, and I'll make a final note that they are not necessarily attached to the axes, but parallel to them. Just as with any vector, we can write the vectors fx and fy in the form vector equals scalar times unit vector. So for example, the fx vector, meaning the x component, is the fx scalar times the I direction, which symbolically is written like this. So you have the I vector as a reference, and the fx scalar is now telling us how long that vector is, and together they tell us the entire component of the x direction of that vector. Similarly, the fy component can be written as a scalar fy for the magnitude of the y component, multiplied by the unit vector j. In summary, we can express the vector f as the sum of the vector component fx plus the vector component fy, and each of those components can be further written as a scalar component times the corresponding unit vector. And so really, we now have really 3 ways of labeling a vector. In the very left side, we have the total vector is expressed in terms of vector component symbols, f vector x, f vector y. In the middle diagram, we have what I'll call mixed. We basically have each component with a magnitude, but explicitly written multiplied by its unit direction. So fx times I, fy times j. And the total vector is now its magnitude f multiplied by some unit vector u. And in the final figure, we have what are called scalar labels, where we simply say the arrow in the figure is implicitly telling us the direction, and we will simply label each vector with its magnitude, fx, fy, or f. And please note there is some difference in the symbols. This is a boldface f, and this is a italicized f.